Right, chapter 6, applications of Newton's law, uh, and plus some examples here. We're going to solve them together, right? So let's take a look. The first topic, friction. So the force that keeps an object from moving horizontally across the table, okay? So it acts parallel to the surface of the table. And there are two types of the friction, static friction and kinetic friction. So static friction is the resist that starts off the motion, and kinetic friction is just slowing down the motion. In other words, if I have right before the motion happens, so this is before, okay, the motion happens. It is about to, the object is about to move, but it's not moving. And, or, you know, you're applying some force to the object, but the object is not moving. The object is resisting, and the resistance is called static friction. Kinetic friction is another type of friction that is happening, but it's for the object that is in the motion, for the object that is moving at this point, okay? So two types of friction, static and kinetic. Coefficient of friction, it's the frictional force, or what we call it as F sub S for static and F sub K for kinetic, is proportional to the normal force. The proportionality constant is the coefficient of friction, which we call it mu S and mu K for each one respectively. And some professors call it mu S and mu K, but I call it mu S and mu K. So, and it is a constant. It is a constant number. It depends on the type of material of which the surface in contact are made. For example, the wooden surface would be different from a surface that is not, that is metal, okay? For example, so it depends on the surface materials. And it is independent of apparent area of the contact between the force. So it is independent of what side of a box, for example, you're using or you're putting on the table. It does not depend on the area. It does depend on the material, the surface structure of, you know, the table, for example. An object will start moving when the maximum static friction force is equal to the normal force, or kind of like that. And we'll get to this in a little bit to kind of go over it in depth. So let's talk about kinetic friction, and then, as I said, we'll go over them. Once the object starts moving, kinetic friction is presented rather than static friction. So static friction is gone because the object is not static anymore. It is moving, and we have a kinetic friction. So it is independent of the speed of the object, does not matter with what speed the object is moving, and is proportional to the magnitude of the normal force. So in other words, we have F of K, mu K times F of N. And if you remember this, we have F of S of max is mu S times F of N. So the only difference between F of S of max and F of K is that we have a coefficient of mu K here, and we have a coefficient of mu S here. And they are different, and they are usually be given to you in a problem. Okay? So let's talk about this. Which one is easier, start a box moving or keeping a box moving? What does this say about a static friction force versus kinetic friction force? So usually it is much more difficult to start the box moving, but once the box is starting to move, the amount of friction is less. Okay, so in other words, let's say that you have a box here. That one's good. So let's say that I have a box, and the box is located right on the surface. So I would have something like this, and I am applying a force, all right, to this box. For example, I am applying a force of, let's say, F to this box, all right? And then what else do we have? The box mass is M. So I have M here, and you know that we have mg down to the center of the earth, Okay, it's a gravitational pull or the gravitational force that has been exerted on the object by the gravity. And then we have a normal force, normal to the surface because it is standing on a surface. So we have a normal force. Or I'm just going to use N. The book is using Fn, so it doesn't matter as long as you're showing it with some number, or N means normal force. And you are applying this force F to this object, okay? But the object is not moving. So the first type is that the object is not moving. Is not moving. All right, in that case, you have a static friction, and it is equal to the force that you're applying to. Okay, so static friction, F sub S, is equal to the force that you are applying to this object, because the object is not moving. You're applying some force to it, the object is not moving. So the friction should be equal to your force, and they have to cancel out, because obviously the object is staying still, does not move, so the forces along the X and Y should cancel out. So in other words, N is also equals to mg. That's what we know. You start increasing your force, okay, and at some point, the object is about to move. The object is about to move. In other words, if you apply even a little bit, just a little bit more force to this object, then it will start moving towards the force, right? To the right, for example, in this case. But in this case, the object is about to move. It's not moving yet. It is, it's just moving a little bit, but it's not completely moving. Okay, so you can kind of feel that the object is about to move, and then at that point, you are dealing with the static friction, which is the maximum amount of static friction. Okay, and that is equals to mu s times n, or mu s times normal force. Okay, and we know that normal force is mg all the time. All the forces along the y direction should always cancel out. That's the maximum amount of friction that an object can tolerate before moving. Okay, that's why we are using max here. And the third type is that once you overcome that maximum friction, once you go a little bit more, you apply a little bit more force to this object, then the object starts to move. The object is moving. Okay, so at this point, then you're not dealing with friction, static friction anymore. You are dealing with kinetic friction, which is mu k dot n, or mu k times normal force. And your normal force is always, no matter what, is mg in this case. Okay, in order to find the normal force, if you don't know, go ahead and watch the videos of the chapter 5. But the forces along the y direction should always cancel out. So it is important to also think about your coordinate system. In other words, if I want to show my coordinate system would be x along this direction and y along that direction. So I have x here and I have y over there. So let me actually go ahead and put them there, x and y. Okay, so let's take a look at this question, lecture question. Slide down. So a box sits on the flat board, as you can see there, and then you lift one end of the board, making an angle with the floor. Okay, so you are making this angle right there, theta, with the floor. As you increase the angle, the box will eventually begin to slide down. Why? So the reason is, let's take a look at these numbers, components, or these options. Components of the gravity force parallel to the plane increase, coefficient of the static friction decrease. To a coefficient of the static friction, mu s, does not depend on the circumstances, does depend on the material and the structure of the surface. So this one is out. This is definitely not the answer. Normal force exerted by the board decreases. And part D, the answer is both number 1 and number 3, or A and B, and that is the correct answer. And I'll go over it one more time to see why this is happening. So if you have a box like that, if you want to take a look at this picture, so if I have a box right here, what I can do, I'm going to rotate it a little bit, making it looking a bit better. And then if I have this side also completed, I am all set. Okay, so let's take a look. So I have a box with mass M, and then I have theta here, the angle. So obviously there is a normal force and a gravity applying in this object. So I have mg down there, and then I have n up there, or normal force up there. Let me actually write it a little bit better because this is important. You know what? I am going to get rid of this and also get rid of this because I want to draw a perfect line and I don't want to draw it like that. So I would say let's try having mg down, having normal force up. Okay, so this is mg and this is the normal force n. Okay, what else do we have? We have a type of friction, okay, that is in the opposite direction of motion. You know, that the friction is in the opposite direction of motion. So if I am, so this will be the direction of motion. So, and then this would be my friction to the opposite side. So this would be my F of K, or friction, and then this would be the direction of motion, right? So kind of like that. Right there, okay? So now what I have here is just a setup. I want to break things to pieces. So now, remember, this is direction of motion. If a force, this is something that I went over a couple times in chapter 5. If a force is not along the direction of motion, it's not along this direction, it's not perpendicular to that, or along this one, you have to get rid of it. You have to break it down to its components. In other words, you have to get rid of this mg here because it is neither along the x and neither along the y direction. So in other words, I can get rid of this mg and write a mg cosine theta here, and I can write an mg sine theta here. It is important to know that the forces along the y direction will always cancel out. So n and mg should cancel out. They are equal. They're in the opposite direction. They will cancel out. And then what we have here is mg sine theta along the direction of motion. Now, the problem is asking us, when this theta is increasing, when this theta is going up, okay, what would happen to the cosine and sine? So cosine of theta and sine of theta, what would happen to that? So when theta is increasing, the sine of theta is also increasing, okay? As we know that sine of theta is always between 1 and -1, okay? So when theta is increasing, the sine is increasing, okay? So that's like that. But when theta is increasing, the cosine is decreasing. In other words, this is decreasing and this is increasing, all right? So which means your mg sine theta gets bigger, or gets big, and mg cosine theta gets small, okay? That's what it means if theta increases, all right? So we have that as well. Let's take a look at this. Static friction, as we said. So I've already talked about it, but I'm going to go over it one more time. So when two surfaces are not sliding across one another, the friction is called static, okay? So you are applying some force of F and the box is not moving. This means that the static friction of the box is equal to the force that you're applying, because the box is not moving, so they have to cancel out. You apply this a little bit more, you're applying a little bit more, and you see the same result. The static friction will be equal to F. You apply a little bit more, and then it is about to move. The movement just begins, okay? It's about to move, it's moving, it's just a little bit, it's about to move, it's the beginning of the motion. At that point, the static friction has reached its maximum value, and it's called Fs of max mu s times Fn. And Fn is this. So Fn, let me actually change the color. Fn is that, F sub n, and this is mg, okay? And we know that the maximum value of a static friction is this. Okay, that's why static friction is always less than equal to that. And the mu s, which is the constant here, is always between 0 and 1. Okay, static friction opposes the impeding relative motion between two objects. Okay, so once it starts to move, then you are dealing with, at the beginning, you're dealing with Fs of max, or the maximum amount of friction that the object can tolerate before moving. Kinetic friction. Kinetic friction opposes the relative sliding motion. Sliding motion, it's moving at this point, okay? Then actually does occur, and it is F of k equals mu k times F of n, or the normal force. Mu k is typically between 0 and 1, and the coefficient, which is called the coefficient of kinetic friction. We have x and y. Okay, I have x and y, and let's see. I want to plot. Okay, so I want to plot, let's say, the frictional force, either the static or kinetic, versus my force that it's been applying to the object. So we know at the beginning, everything that I apply will be equal to the frictional force as a static friction. And it reach a maximum point, okay, which is called the F of max. And then it will drop a little bit. And then whatever force that I apply, the object at this point is moving, my frictional force would be the same. So this is the kind of sketch that you can make. So this is an angle of 45 degrees, okay? This is the maximum point. So F of s of max, which is mu s times n. And this is just F of s, which is equal to the F of s, which is equal to the F that I am applying. And at this point, I have F of k, because the object is moving. No matter how much extra force that I exert on the object is moving. F of k does not depend on the acceleration or velocity, and it's always mu k dot n, or times normal force. Okay, so sleds. The sled comes to a halt because the kinetic frictional force opposes motion and causes the sled to slow down. As we know, the initial velocity here, v0x, is 4 meters per second. After spending some time going the distance of x, it comes to rest at the v of final, or v of x, equals 0 meters per second. The reason for that is that we have a frictional force. So we have a frictional force, F of k, that is in the opposite direction of motion, killing all the energy, transforming the energy that this guy has on the sled to the thermal energy, and you know, that's why it's halting and stopping after some time. Okay, so suppose the coefficient of kinetic friction is 0.05, so mu k is 0.05, and a total mass is 40 kilograms. So the sled plus that guy and the kid on top is 40 kilograms. So M is 40 kilograms, okay? What is the kinetic frictional force? In other words, we want to find this guy, which is the opposite direction of motion. What is F of K? So we're looking for F of K. Obviously, it is F of K because the object is moving, okay? Otherwise, we would just have F of S. Now, if that's the case, I know what the F of K is. F of K is mu K times normal force. But what is the normal force? Normal force, let's see, we have mg down here, always towards the center of the Earth, and the normal force is normal to the surface, and it is this guy. The forces along the y direction will always cancel out. In other words, N is always mg, which means I can use it right there. And if that's the case, I can just substitute mg for N. So mu k dot mg is the answer. So if that's the case, now I have F of K equals mu K, which is 0.05, times N, which is 40, times G, which is 9.81. And then whatever this F of K is, you can find it, you can put this in the calculator and find it. Whatever it is, it will be in terms of newtons, okay? It's a force. So it has to have the units of force, which is newtons, okay? Okay, we'll go to tension next in the second part of the video. This is the end of part 1. We'll continue our work with part 2.